Cloud. Okay, that's fine. It is recording now. Okay, let's see what we learned in our last class. Before we start, let me share my screen. Okay, so now we are. Okay, let me turn off the video, then it will be more clear. Let me turn off the video. Okay, now it is fine. Let's take the video and then okay, let's go through. Okay. Currently, we are working on the process process management or process scheduling algorithms. It is from our RAM to CPU or memory to CPU. This is the CPU. Okay. Currently working on the process management system or process. How to schedule the process to CPU, and we know that we learned the short job fast scheduling algorithms or SJF. At the beginning we learn, and then we learn another algorithms. It's called SRTF algorithms, short remaining time fast algorithms, and this is short job fast algorithms. Okay, this is non-preemptive algorithm. This is preemptive algorithms, and then we learn another algorithms is called the LJF, longest job fast algorithms, and LRTF, longest remaining time fast scheduling algorithms. And then we also learn one algorithm is called FCFS, fast come fast serve algorithms. And also in our last class we talked about the we talked about the priority based. We learned the priority based scheduling algorithms. Priority based scheduling algorithms. Algorithms. Okay. So far we know about this type of algorithms. Here, as I mentioned, that this is non-preemptive. This one is non-preemptive. Also, this one is non-preemptive. Also, priority-based algorithms. In our last class, we saw that in a process ID, every process ID, when you're operating, when you click a process, when you open a program, your operating system will make a system call and create a process. Okay, and it assign the process ID, of course, process ID. Also, it's assign a priority number for for this process. Okay, and one is of course the process ID and priority number. Okay, priority number. Okay, priority number, and then this algorithm also based on this priority number, your operating system will schedule the CPU for a specific process. Okay, this priority number, this priority based algorithms can be two types. One is also this can be preemptive version as well, also non-preemptive as well. So this is also preemptive. You can say here this is preemptive, this is preemptive, this is preemptive. Also here also there is preemptive version is available. Okay, preemptive priority based algorithms available. Okay. Also, what is non-preemptive algorithms in here? This is sorry, these are all are non-preemptive. Now, what is the preemptive based algorithm? This one is this one is preemptive. This one is preemptive based algorithm. Also here, priority based algorithm. Also one is non-preemptive, Another it can work as another version can be preemptive as well. Preemptive as well. Okay. So this one is primitive, this one primitive. Also here, that one is also primitive. Okay. One thing you also know that primitive means that once you schedule a process, your CPU can forcefully stop the process. Okay, when highest priority process inside the RAM. And non-primitive, once you schedule a process to CPU, your CPU cannot forcefully stop this process until it completes its execution. Okay, this two term is very important. You need to actually note about this. Okay, primitive and non-primitive. And also in our last class, we complete till priority-based scheduling algorithms. In our today's class, we also see two other algorithms, two new algorithms. Okay, we'll discuss two new algorithms. Let's see what are others two new algorithms. Okay. Okay, so now our first algorithms today we learn. The first one is the highest response ratio next. But I'm saying that it is highest response ratio next. From here, it's make a acronym. It's called the HRRN. Okay, scheduling algorithm. Okay. Highest response ratio next. HRRN scheduling algorithms. Okay. Now let's see how it works. Okay. It is very interesting algorithms. Very interesting HRRN. Okay, let's see how HRRN works. Okay. Okay, at first, let's see what is the HRRN and its properties. What are the properties for HRRN? Yeah, HRRN is also HRRN is non-preemptive algorithms. Non-preemptive algorithm. This is one property. Non-preemptive algorithms. Okay. Algorithm. It is non-preemptive algorithms. Also, it uses one response ratio. Yeah, you see this highest response ratio next. Okay. So how to here this ratio. Okay. Here you mean how to calculate the response ratio. Let's see how calculate the response ratio. The equation of response ratio is nothing but response ratio is equal W plus E divided by E, where W equal waiting time and E equal execution time. Okay. Okay, these are the two things to calculate the response ratio. Okay, to calculate the response ratio. Here, to implement the highest HRRN scheduling algorithms, you need to calculate the response ratio first. Okay, the response ratio equation is W plus E divided by E, where W is the waiting time and E is execution time or burst time. Okay. Now let's see how it works. So after calculating the response ratio, and among the available processes means among the available processes inside the RAM or memory, which has the largest response time will be scheduled first. Actually, which has this biggest ratio will be scheduled first. You calculate the process. Let's say three process inside the RAM: P1, P2, and P3. currently inside the RAM, and you calculate this response ratio among these three processes, and from this response ratio, actually the highest response ratio will get the CPU first. Okay, this is why its name is highest response ratio next scheduling algorithms. Okay, so from this response ratio, you calculate from this response ratio, your algorithms schedule a process from the RAM to CPU. Okay. Okay. So here response ratio is important. Now let's check some properties of this response ratio, actually how it works. Okay. You see here actually it takes two important things. Actually, it gives the two important messages. One is it's favor the shorter process. The process shorter process means the actually small burst time or execution time. Okay, short burst time or execution time. That is the meaning here. Meaning for the shorter process. Okay, it's actually favor the shorter process and limits the waiting time for a longer processes. You see that when a process execution time is when execution time is actually short execution time means the shorter process. When a process actually contains a short execution time, that time you may calculate by yourself. When execution time is actually small or and let's say two process inside the RAM, it takes 3 nanosecond. It takes 300 nanosecond. Okay, 300 nanosecond. It arrives uh, at a actually same time inside the RAM. And if you calculate this ratio, the small process, this response ratio will be the P1 will be the highest. Okay, P1 will be larger than the P2. Okay, P2, because here E is smaller than the process P2. Okay, P1's execution time is smaller than the process P2. So this P1 response ratio will be high. Okay, if you calculate the response ratio, P1 will be the high than the P2. But if P2 is wait for a long time, that time its waiting time will be increased. Okay, if it is increase, and some amount of time, then also P2's ratio will be high because waiting time will be higher. So from here you can see it is interesting. It gives the actually shorter process priority. Shorter process favors the shorter process if among the available processes. It gives actually favor for the shorter process. Also, it limits the waiting time. A process may not wait for a process actually may not for starve. Okay, starvation. You know the starvation problems already. A larger process actually may not starve. Okay, because it is waiting. If it is waiting a certain time limits, cross the certain time limits, and after that its response ratio will be higher. Okay, because W here one also a parameter is also waiting time as well. Okay, when W is increased, also this ratio will be increased. Okay, this ratio will be okay. So there is a less chance a process may actually stuck into a starvation problems. Okay, this is how these algorithms works. Okay, so here these algorithms, it's actually it favors shorter process. Of course, the when mm, among the level process, it gives the shorter process. Also, what it does, it limits the waiting time for a longer process. Okay, it limits waiting time for longer process. Okay, a longer process may not actually suffer by the starvation problems. Okay, starvation problem. It can actually uh, it can avoid these starvation problems if you use this HRRN algorithms. Okay. Now let's see one example for HRRN algorithms. Then it will be more clear to you how it works. Okay, now let's check one example that we did previously for other algorithm, SGF, LGF, and SRTF. Okay, now here one thing is that let me again run the let me again write the response ratio. Response ratio is nothing but W plus E divided by E. So which response ratio is highest will get the priority. Okay. Now let's we have total 5 process. We have total 5 process, and of course we have the process ID. Process ID. We have total 5 process. We consider in here P1, P2, P3, P4, and P5. Okay. We have total 5 process. P5. Okay. Now let's check its arrival time. Arrival time of each process and its execution time. Okay. It's execution time. Arrival time for process P1, let's say 0, 2, 4, 6, 8. That's it. This order. The process actually arrives into the RAM. Okay. And its execution time, process P1 execution time, let's say 3 time in, let's say nanosecond, 3 nanosecond. If it is microsecond, then 3 microsecond. Okay, let's check. Let's consider time unit as a nanosecond. Okay, 6 nanosecond. That one is for 4 nanosecond, 5 nanosecond, and 2 nanosecond. Okay. Okay. Let's now let's draw the Gantt chart for HRRN algorithms. Now we are talking about this is the example for HRRN. Okay. Highest response ratio next scheduling algorithms. Okay. What is the Gantt chart in here? Let's see. Let's see the Gantt chart here. At time unit 0, how many processes inside the RAM? At time unit 0, only one process inside the RAM. If you look at in here, only we have only one process. Okay, only one process. It is nothing but process P1. Okay, process P1. So P1 will be scheduled by your operating system, and then also one property I mentioned earlier that this is non-preemptive scheduling algorithm. So your CPU cannot preempt this process until it completes its execution. Okay, it takes 3 units of time to complete its execution. So process P1 will be complete in here. Okay, time unit in here, process P1 will be complete, and then at time unit 3, how many processes inside the RAM? Only process P2. Only process P2. P3 will be arrived at time unit 4. So P2 will be scheduled by your operating system. Also, it will complete. It takes 6 unit of time. So 6 plus 3, and it will complete at 9. Okay, at 9. And now let's check that how many processes inside the RAM. Here you can see we have total all process inside the RAM. Okay, now this all process now currently inside the RAM. This process P5 will be arrived at time unit 5. Okay, time unit 8. Time unit 8. Okay, here time unit is current time is 9. Okay, so all process currently inside the memory. So how you your operating system will schedule the process from among the three processes. Okay, how to select your operating system a process from the RAM, and it it will schedule to the CPU. How to select that one? if you consider this HRRN, you need to calculate this equation. You need to actually determine this equation for every processes. Let's check this ratio, response ratio for process P3 at first. How to calculate this response ratio process P3? Here you can see, let's say response ratio P3 process P3. What is the how to calculate it? It's first it's waiting time. Okay, waiting time. So how to calculate this waiting time? From here, the process arrives at time minute 4. Now, here is time minute is 9. Okay, time minute 9. So how long it's already wait? 9 minus 4 is 5. So 5 time minutes already. Its process is now actually wait inside the RAM. Plus its execution time. Execution time is 4. And divide by also execution time. We have this execution time. Okay? Also 4. Okay. Now let's see, it is 9 divided by 4. So let me check with the calculator. What's the value? Okay. It is 2.25. Okay, 2.25. This is the ratio for process P3. Okay, HRRN response ratio. Okay. Now calculate the response ratio process 4 P4. Okay. So how to calculate this? RR4 response ratio for process P4. Okay. So how to calculate this one? So let's calculate the how long process P4 is waiting, currently waiting. Okay. At first we need to figure out the W or waiting time. Okay. So how long it's wait? It arrives at time minute 6. Current time is 9. So 9 minus 6 is 3 time minutes. It's currently waiting, and its execution time is 5. So 3 plus 5 divided by execution time 5. Okay. 3 plus 5 divided by 5 execution time. Okay. Now 8 divided by 5 is nothing but 1.6. Okay. 1.6. Okay. Next, you need to calculate the response ratio time for process P5. Okay, process P5. So let's see how long the process P5 is currently waiting. It's arrived at time unit 8 and current time is 9. So 1 plus its execution time is 2 divided by 2. Okay, it is nothing but 3 divided by 2. It is 1.5. 1.5. Okay. So among this process, which process will be scheduled next? Which has this highest response ratio? Okay. Which has this highest response ratio? Here the highest response ratio for process P3. So your operating system will schedule the process P3 next. Okay. P3 next. How long it will execute? It will execute its 4 time units. So 9 plus 4 is nothing but 13. Okay, 13. So it will execute till process 13. And next is, and now clock is time 13. Next, which process will be scheduled? So again, your operating system needs to calculate this response ratio. Okay. Now, how many processes inside the RAM? Currently, we are executing a complete your CPU executed this process, that one also P3 is done. Okay, now we have process P4 and P5, right? So how to calculate this response ratio for process P4 and P5? Again, your CPU, your operating system needs to calculate this response ratio for these two processes. These are done. So now P4 and P5, let's calculate the response ratio for process P4 and P5 again. So RR for response ratio for process P4. So how it looks like? Let's see. At first, you need to calculate how long it's this process P4 is now currently waiting inside the RAM. It's arrived at time unit 6. Now time is 13. 13 minus 6 is 7, and plus its execution time is 5 divided by execution time 5. Okay, it is 12 divided by 5. 12 divided by 5. If you divide it, it becomes 2.4. Okay, now let's calculate for response ratio, current response ratio for process P5. Okay, P5. At first, how long it's currently waiting? It is 13 minus 8 is 5 plus its execution time is 2 divided by 2. Okay, it is 7 divided by 2 is nothing but 3.5. Okay, 3.5. Okay, so among this between these two processes, which actually has highest response ratio? This is nothing but process P5. Okay, P5. Process P5 has 3.5. Process P4, its response ratio is 2.4 now, currently now. So which process will be scheduled by your operating system? It is process P5. Let's check process P5. Okay, let's go through process P5 now. Process P5 is currently scheduled by the CPU. So it takes, here you see how long it will take. It will take 2 time unit. So it's 15. It will stop at 15, complete its execution now. Now we have only one process. This is nothing but process P4. Okay, P4 will be completed, will be scheduled next, and it takes total 5 time unit. So at 20, it will complete its execution. Okay. Okay. So this is the Gantt chart for HRRN algorithms. Okay, it is very interesting algorithms. You need to calculate this response ratio. Okay, to figure out this process table. Sorry, this Gantt chart. Okay, now next also you may this things is easy. Let's you may calculate the sorry you may calculate the complete CT as well as the turnaround time as well. Let's check what is CT and TAT. That is CT completion time and also turnaround time for HRRN. Okay, turnaround time. Okay. Now CT is when actually it completes execution. If it completes in here at time unit 20, the 20 should be in here, and P5 completes is 15. P5 is 15, and then P3 13, then P2 is 9, and P1 is at timing 3. Turn around time is nothing but the completion time minus arrival time. Okay? Here is 3 minus 0 is 3, and then 9 minus 2 is 7, 13 minus 4 is 9, and 20 minus 6 is 14, 15 minus 8 is 7. Okay, this is the turnaround time CT and TT for HRRN algorithms. Okay. Okay, do you have any questions or comments regarding HRRN algorithms? Okay, if you do not have questions, let's move forward. And we have this. This is our final algorithm for process scheduling. Okay. Okay. Let's see what is the next algorithms. Okay. Next one is the round robin. We learn the round robin scheduling algorithms. Okay. Round robin scheduling. Or you can hear at short, you can say the RR, round robin scheduling algorithms. Okay, round robin scheduling algorithms. You have to take a note. It is very actually important algorithms because it is most popular algorithms nowadays. Almost all operating system follow the round robin scheduling algorithms. Okay, that's why it's very popular as well as the most popular also this currently almost as I mentioned currently almost all operating system use the round robin scheduling algorithm. Okay? Algorithms. Okay, its structures and also yeah, selection structure is different from others algorithm. Selection structure select the process schedule a process to CPU is different than the others algorithm that we learned already. Okay, it is little bit different algorithms, but it is very effective, also very popular, very popular algorithms. Okay, let's see how it's work. Round robin scheduling algorithms. So before we start the round robin scheduling algorithms, the round robin scheduling algorithms, it use one thing is called the time quantum. Okay, time quantum. Let's see what is the time quantum. It's called one term is called the time quantum. Okay, time quantum. Okay, time quantum is nothing but maximum allowable time. Maximum allowable time a process can run without getting printed. Printed. Okay, printed. Okay, without getting printed without getting printed from CPU. Okay, CPU print your process. Okay, so this is the maximum time quantum is maximum allowable time. Max time. Okay, max time for a process that can run without getting preempted means that once you define your round robin scheduling algorithm define a time quantum, let's say 4, 6 or 2, whatever it is time quantum. So if you schedule a process, you know this always higher priority process inside the RAM. But once you schedule a process, it can execute your CPU must execute this process this minimum time quantum. Okay, sorry, this maximum time quantum. Okay, this maximum time quantum. It's of course it will execute in maximum time quantum before get printed. After execute this maximum time quantum, then actually this process will be printed if another process is available inside the RAM. Okay, then maybe you get the point that how it works. Once you schedule a process, once your operating system schedule a process to CPU, it runs at maximum maximum time like 2. And then if you set this time quantum 2, so it will run 2 time unit, then it will get the printed. Okay, yeah, at 1 time unit it won't be printed if it needs the execution time 2. Okay, 2 time unit. So at least it will executes once it gets chance to CPU. At least it will complete its execution till maximum time quantum. Okay, maximum time allowable time. Okay, this max time. I'll come in later this what is the max time mean. Okay, also this is the also time quantum. So when uh, when your process get printed, this is the another thing. Okay, this is time quantum. It is fine. Mm, fine. So when actually it will which purposes it will get the printed. What is the priority or what is the it does it is it depends on the execution time of other process or some other parameters. Okay, we need to know about this. So it is a combination of time quantum. It is combination of time quantum. Round robin is a combination of algorithms that combine this time quantum plus FCFS. Okay, FCFS, first come first serve. Okay, time quantum plus first come first serve. From here you also get the idea. It will once the process inside the RAM, it will schedule and it will run till allowable time quantum, and then if another process is available, then it will also schedule next, give the chance to the CPU, and it will execute till till the allowable maximum time or time quantum. Okay, time quantum, and then again it will execute. From here you can see that here it use if you think about the implementation, it is first come first serve. Also the time quantum is fixed for design your operating system. When you design your operating system, you can fix the time quantum. It uses the round robin scheduling algorithms, and this process, and then it applies the FCFS, first come first serve. It doesn't depends on your algorithm. It doesn't require to uh, know the total execution time or burst time. So it is very easy to implement. Okay, but also this is very effective algorithms. Okay, compared to others algorithms. Okay, now let's see how it works. Another thing is that this round robin scheduling algorithms, this round robin scheduling algorithm, it works within a queue data structure. Okay, to implement the FCFS, FCFS means the first come first serve. Also queue, you also know about this queue. You may you also familiar with the queue data structure. Queue data structure. Queue is nothing but also first come first serve, or it is also known as the FIFO, first in first out. Okay, first in first out. Also in CPU, it is also for operating system, it is considered as FCFS, first come first serve. In other data structure, for queue is also known as the first in first out. Almost this is almost this equivalence. Huh? So in round robin algorithms, it is used a queue data structures. Also, you know that queue is nothing but first in first out or first come first serve. Okay, queue data structures. It is a queue data structures. Keep in mind. Okay, it is a combination of time quantum plus FCFS. Also, it uses queue data structures. Okay, now let's see how this FCFS works. One example I will give you. One example how it works. Okay, from a process chart. Okay, let's see. We have total. Let's consider we have total 6 processes. Okay, we have total 6 processes. This process table. Also, not process table actually. We can see the process chart or something like this. Process. Okay. Let's say what is process ID. Now, process ID is from P1. We consider the total 6 processes. Okay, P2, P3, P4, and P5, P6. Okay, total 6 process, and its arrival time and its execution time. Okay, execution time. Now let's see the arrival time of this process. It's as usual 0, 1, 2, 3, 4, 2, 3, then 4, 6. Okay, let's consider this order. The process comes into the RAM. Okay. Also, this execution time for process P1 is 4. Here it is 5. Here it is 2, and then 1. Here it is 6, and there is 3. Okay. This is the execution time of the process. Now, variable time as well as the execution time. Okay, of a process. Total 6 processes. Now let's see that how RR algorithm, round robin scheduling algorithms work. Okay, round robin scheduling algorithms work. We, as usual, we'll calculate the we'll draw the Gantt chart, and we need to maintain a queue data structures. Queue data structures to actually satisfy the first come first serve. Okay. Now, okay, another property is time quantum. Okay, this is important thing. Okay, how about the time quantum? Let's consider time quantum for this algorithm in here. Time quantum. Time quantum. Let's consider two. Here two. Okay, two time unit. Okay, means that once you schedule a process to CPU, it will execute two time units. Okay. Now let's check how it works. Okay. This is the queue data structure. You always know this queue will be inserted from the rear end, and it will be removed from the front side. Okay, first side. So it will be the first in first out, or first come first serve. Okay. Now this is the Gantt chart. This is Gantt chart. Consider in here the Gantt chart. Gantt chart starts from 0 because of 0. At 0 time unit, how many processes inside the RAM? Only one processor, P1. So P1 should be inside the queue first. Okay, at the queue, because at 0 time unit only one process. So only one process inside the queue. Okay, so this process will be removed to schedule the CPU. The operating system will find at time 0 unit only one process inside the queue. Okay, only one process inside the queue. So this process will be removed by your operating system and will be scheduled to the CPU. Okay, and P1 will be in here. So how long it will run once it's actually scheduled? It will run till two time unit. Okay, till two time unit. It will run two time unit. So here is two. Before get the primitive. Okay, primitive. Otherwise, after two time unit, then you need to check this how many processes inside the RAM. Okay. Now let's check this how many processes inside the RAM after two time units. This is process at two time units. There is process P2 and also process P3 inside the RAM. So P2 and P3 will be added to the queue, P2 and P3 in the queue at time unit 2. Also here your P1 needs 4 time units. It completes 2 time units currently. So here it will be it will needs another 2 time units, right? It will needs 2 time units to complete its execution. So P1 is still your P1 needs the CPU. Okay, needs the CPU. It is not completed yet. Okay, so what's your operating system will do? This P1 again, P1 back to the queue. Okay, P1 back to the actually last. It will not be not the first, because P1 already get the CPU. P1 already get the CPU. So you need to actually the operating system need to get the chance for process P2 and P3 first. Okay, then actually that's why P1 P2 comes in here, and P1 will be moved then next to P2 and P3. Okay, now what your operating system will do? Operating system will take this process out of this process, and it will schedule to the CPU. Okay, and then how long it will run? It will run till 2 time units. Okay, 2 time units. 2 time units. So here 2 time units is done. So it needs another 3 time units to complete its execution. Okay. So now sorry, here is 2 plus 2 is 4. So at 4 time units, how many processes inside the RAM? You see, process P4 and P5 also inside the RAM. Okay. P3 here is 3 time unit and 4 time unit. P3, P4 and P5. So P4 and P5 added to the queue Also, P2 is still needs 3 time unit. It will also back to the queue as well. Okay, P2 in here. Okay. Now, push process P3 in front of the queue. So P3 will be removed and it will schedule to the CPU. It's P3. How long it will execute? Let's say P3. How long it will execute? It will execute 2 time units. So it is 6 now. Here you see that P3 needs 2 time units. Okay, 2 time units. Okay, so at 2 time unit is complete with execution. Okay, complete execution. So it doesn't require to back to the queue. It's already complete. So it is fine. Now let's check this, how many process inside the RAM. Here is this process already inside the RAM till 5, 6 also. Now time is 6. The process P6 also inside the RAM. So P6 will be added to the queue now in here. Okay, and then P3 will not back to the queue because P3 completes its execution. And now which process will be removed? Then again P1 will be in front of queue. It will be scheduled in here. P1 will run another 2 time units. 2 time units. It is 8 now. So and you see that its remaining time was 2. So it's completes execution. Now also no process at 6 every process inside the RAM. So no worries about this, that how many processes inside the RAM. All processes currently inside the RAM. It's fine. So next, which process will be removed? Process P4. Okay, P4 will be scheduled. Now let's check process P4 how many time units it needs. You see, process P4 needs 1 time unit. 1 time units to complete its execution. This is very important point. 1 time unit. Process P4 needs 1 time unit. So it will it take the time quantum till 2 till completes it will till go till 10 plus 2 it will complete 10 because it needs 1 time unit. 1 time unit. But it is not like this. At the beginning, I mentioned that round robin time quantum is maximum allowable time. Okay, maximum allowable time, max allowable time. That's why it is max allowable time. Max allowable time is 2, but here this process needs only 1 time unit. So it will never take 2 time unit. This is about maximum allowable time. If it is required 2 and more than 2, then it will go for 2 time unit. But if it requires less than this time quantum, so it will run till its execution time. So it will run till 1 time unit. Okay, it will be 9 and completes its execution. Okay, and then his process P5. P5 will be scheduled in here, and P5 needs how many time? Okay, P5 first time it gets the CPU. Okay, P5 first time it gets the CPU. I saw, yeah. So it's done. Now it's 4. Another it needs 4 time units. Again in here. Now again P2. P2 in here. Oh, P5 again actually backs to the 10 because it needs P5 should be in here. Okay. It doesn't complete it here. P5. Okay. That's why it's back to the queue. Okay. And then P6. Sorry, then P2. Okay. P2. Now P2. Just pressing here P2. P2 needs 3 time units. Okay. 3 time units extra, so it will complete 13, and it needs another 1 time unit to complete its execution. Okay. Again, it is not complete, so it will back to the queue as well. P2. Okay, P2 back to the queue again. Now let's check which process is next. P6. Okay, P6 will be scheduled, and P6 need P6 get the first time CPU. It will take 2 time units. It will be 15 in here, and here it will be 1. It needs another 1 time unit to complete its execution. Okay, so P6 again it will back to the queue, and then which process will be comes next? P5. Okay, P5 now checks how long it will needs to complete its execution. Okay, P5. P5 needs another 4 time units. Okay, 4 time units. So it will goes to 17, and here it needs another 2 time units. So P5 also back to queue again. the P5 in here. And next, which process? This process is process P2. Okay, process P2. We say process P2 needs maybe one time unit. Okay, one time unit. So it will be 18, and then it's completes its execution. Okay, it is done. So it went back to the queue. Now we have P6. P6. P6 needs another one time unit. So it will be the 19 in here, and then it completes the execution. It's complete now, P6 complete, and then we have P5. Okay, P5 needs two time units more. Okay, then P5 and 21. Oh, done. The process is done. Okay. Okay, so this is the round robin scheduling algorithms. Again, I repeat, this is very important. Sorry, this is very actually popular algorithms. Okay? It based on the FCFS. From here, how we can observe? We can observe that it is works in basis of time quantum as well as the FCFS. Also, every process almost gets the equal priority. Okay, it depends on FC, first come first serve. Also, it is the time quantum, another parameter, maximum allowable time quantum. Okay, so from here you can observe that observe that if time quantum is increase or decrease, context switching of this process of the increase and response time of a process. Okay, so if the time quantum is increase, that time actually context switching, that switching between one process to another process. Okay, and another process. We have lots of switching. Huh? The two time units and then again two. But if you increase the time quantum 2 till 4, so at 4 process P4 actually completes the execution. So you don't require to again P3 to you don't require to actually back to the processing to the queue. Okay? You don't require. So context switching will be the less. Another thing is that it may increase the waiting time of the process. If you increase the quantum time, of course, if you want the quantum time increase, then this process first time get the CPU after 2 time unit. But if your quantum is 4 time unit, this process will get the CPU after 4 time unit. So waiting time will be increased. Okay. Okay. This is another thing you need to keep in mind that for round robin. Now let's see what is the advantage of round robin scheduling algorithms. You know that this is not a priority based algorithm. Okay, it depends on the first come first serve or some constant time quantum. So it is not a priority based scheduling algorithms. So there is no starvation problems. Okay, there is no starvation problems. Also, there is no convoy effect problem as well. The process needn't actually wait for a long time because it depends on the time quantum. Okay, it depends on the time quantum. Okay, it doesn't require to wait for it to complete execution for a big process. Okay, it is not such a case. It is depends on time quantum, so there is no convoy effect problems. Also, this is practically implementable because this is on constant time and this is FCFS. Okay? This is practically implementable. Also, there is good response time as well. Response time at first, response time means that for all processes inside the RAM and when actually it gets the CPU first. Okay. So in here, whatever the quantum time, depends on the quantum time, response time will be, of course, increase or it will be good. This algorithm provide good response time for these processes. Okay. Also, some limitation. It is not a drawback. You can say some limitation. Throughput is still good. Throughput means for a particular time unit, how many process complete its execution. Okay, but throughput is good for round robin scheduling algorithm, but it may less. Sometimes it may less if you compare the FGF and SRTF, but it is not actually two ors. Okay, it is almost sometimes almost similar, but if you use many smaller process, that can you may find some difference between FGF and round robin, but still throughput of round robin is still very good. Okay, but FGF and SFTDT is not a practically implementable algorithms. It use something called the burst time or execution time. It is very difficult to predict at the uh, beginning the total execution time for a particular process. Okay, but in case of round robin, it is practically implementable because it depends on the time quantum as well as time quantum as well as the first come first serve. Okay, also it maintain one data structure is called Q. Q is nothing but from here. Q is nothing but used to maintain the FCA. Okay, used to manage the FCA first come first serve. Okay. Okay. So any questions regarding round robin distributing algorithms? Okay. You do not have any questions. So in our next class, we will start to learn the thread. Okay, thread. We didn't study the thread yet. This is very important topic for operating system. So from our next class, we learn the operating systems thread. Okay, it is very interesting. So we will start from again. We will just review some topic from PCB process control block, and then PCB process control block of PCB, and then we will start learning the thread. Okay, operating system thread. Okay, the next part we will start. Okay. Uh, so if you do not have any questions or comment, we can stop here and see you next class. Have a good evening and good night.